This is another example problem that shows the combination of both rotational dynamics and rotational kinematics. So we have this toy top with this spool where you're going to pull the string in order to get the toy top to start spinning. And what we're looking for this problem is the time that it takes to complete the first 5 revolutions for the toy. So what we know here is we know the diameter. So the diameter of the toy is 5 centimeters. We know the moment of inertia is 3 times 10 to the negative fifth. That's kilograms meters squared. We also know that the tension, I'm going to call it F sub t for the force of tension, is 0.3 newtons. And we're trying to figure out the time that it takes to spin. Well, what I'm going to do is this. I'm going to say that, all right, since the diameter is 5 centimeters, that means the radius is going to be 2.5 centimeters, so 0.025 meters for the radius of this toy top. Since I know the moment of inertia, I know the radius, I know that force of tension, what I can do is I can find the torque due to that force of tension. So the torque due to the force of tension is just equal to the force of the tension times that radius. Because it's spinning around the center, and that's its rotation axis, that's going to be the radius that we're going to use for the distance of the torque to the center of rotation. So if we take a look at what we have here, the torque that we have is going to be equal to 0.3 newtons times the 0.025 meters. And if I multiply those together, so 0.3 times 0.25, that's going to give us a distance, or I shouldn't say a distance, a torque value of 0.0075 meter newtons. Now, the next thing that I can do here is, since I know the torque, and I also know the moment of inertia, I can figure out the angular acceleration, because the angular acceleration is equal to the net torque. In this case, it's just that torque of tension divided by the moment of inertia. So if I were to plug in the values, I know my torque is 0.0075 meter newtons. I know the moment of inertia is 3 times 10 to the negative fifth kilograms meters squared. And if I solve this, 0.0075 divided by 3 times 10 to the negative fifth, I get 250, and that's radians per second squared for that angular acceleration. Since I know the angular acceleration is 250 radians per second squared, and I'm trying to figure out the time for the first 5 revolutions, what I'm going to do is this. I'm going to use my angular displacement equals my angular velocity times time plus 1/2 times the angular acceleration times the time squared equation in order to figure out what my time is. Now I know that delta theta is going to be 5 revolutions that I'm looking for. So it's going to be 5 times 2 pi radians equals, well, my initial angular velocity is just 0 radians per second times t plus 1/2 times 250 radians per second squared times t squared. And I'm just going to solve this for t. Well, I know 0 radians per second times t, that's just 0, so that cancels out. So basically I'm just taking 10 pi, dividing it by 125, which is what I get from 1/2 times 250 radians per second squared, then the square root of that. And what happens is I get a time of 0.501 seconds when I do that. Well, that's my answer. So it takes 0.501 seconds, which makes sense if you think about it from just a realistic point of view. When you pull the string in that toy, the toy starts spinning pretty fast, so it doesn't take a lot of time for it to spin those 5 turns. But we're done at this point.